ever noticed how fast children's legs seem to pump when they ride their bikes? Even if this child were to keep up with her mother, traveling the same speed and the same distance, her little legs would have to go around many more times. This may seem curious, but it occurs because although she's moving with the same linear velocity, she does not have the same angular velocity.
Isn't that just because she doesn't have the same length of legs as her mother?
Well, only indirectly. It occurs really because the bicycle wheel of the child is smaller, and of course that's because her legs are shorter.
I'm not sure I understand why she would have to pedal faster, though.
Well, let's back up and define angular velocity. Angular velocity measures the rate of rotation of a point about a fixed center. That is, it measures the rotation angle per unit of time when an object is rotating about a center point. So an angular velocity of pi over 4 rads per minute would mean
that it was moving pi over 4 radians per every minute?
For every minute, exactly. The formula is angular velocity is equal to theta in radians divided by time in whatever unit you care to work with. So let's compare the angular velocity of the mother to that of the child. So earlier, we'd measured the diameter of each bicycle wheel, and we found that the adult bicycle had a diameter of 69 centimeters, and the child's bicycle wheel had a diameter of 58 centimeters. Okay, so the first thing we need to do in order to calculate the angular velocity is what?
We would need to find the circumference of the both wheels.
Right, because we need to find out how many rotations the bicycle wheel is making in a particular unit of time. So what we're going to do is find the circumference of each wheel. Circumference, of course, is equal to?
Pi d.
Pi times diameter. So the circumference here would be?
69 pi.
69 pi, and we could transform that to a decimal, but it's equally okay to leave it as 69 pi. The child's bicycle wheel then has a circumference of?
It would be 58 pi.
58 pi. So what we need to calculate now is?
How many revolutions it made in the distance.
In the total distance. And the total distance they traveled, incidentally, was 40 meters. So then the number of revolutions she would make in 40 meters would be what? How would we calculate that?
Since this is still in centimeters, we would have to use 4,000 centimeters.
Right.
And divide it by the circumference of the wheel, which is 69 pi.
69 pi. Now, that gives us the number of revolutions. How are we going to transform that into an angle measurement in radians?
We can just times it by 2 pi.
Multiply that by 2 pi. And what do we get for the number of radians?
115.94 radians.
0.94 radians. And what about the child, just to do a comparison here?
We would divide 4,000 centimeters.
Right, divided by?
58 pi. And times it by 2 pi again.
And we find that the child's bicycle wheel has rotated through?
137.93 radians.
0.93 radians. Now, that's not our angular velocity. We need to take that measurement now and substitute it into our formula. The total time it took them to cover those 40 meters was 10 seconds. So the angular velocity of the mother, theta divided by t, is?
It would be 115.94 radians divided by 10 seconds.
Divided by 10 seconds, which of course then is?
11.60 or 594
radians
per second.
Per second. And similarly, the angular velocity of the child
would be 137.93 radians
divided by, again,
10 seconds.
The time, 10 seconds. And we get
13.793 radians per second.
Right. And so we can see that the child has a greater angular velocity. That's why her little legs are pumping faster.
Just when is it necessary, though, to be able to have to look at angular velocity?
Well, a second example would be the odometer of your car. The odometer of your car is set to calculate the number of revolutions for a given tire size. So if you change the size of your tires, either increase it or decrease it, your odometer is no longer accurate.
Archimedes, who lived around 250 BC, was the first to calculate the value of pi. He estimated pi to fall somewhere between 3.1408 and 3.1428. He also proved that anything that really exists, no matter how large, can be counted or measured.